Let's look at an example of projectile motion, and the simplest example would be one that has a horizontal launch. So in this example, let's go ahead and read it real quick. A movie stunt driver on a motorcycle speeds horizontally off a 50-meter high cliff. How fast must the motorcycle leave the cliff top to land on level ground below 90 meters from the base of the cliff? Okay, so this guy is speeding along the top of the cliff. He leaves horizontally, and we'll trace a pathway to the ground that is going to look something like that. In order to do these types of problems, pictures are very important. I'm going to actually draw in right now the initial velocity vector the motorcycle has when it leaves the cliff. Okay, so this is the initial velocity of the motorcycle, and that's actually the thing we're looking for. I'm going to put a little question mark there. Now, what do we know? We know that the cliff is 50 meters high, and we know that we want it to land 90 meters from the base of the cliff. Okay, now we have information, but like in all our other problems, we need to turn these into some variables we can use with equations. So this is a vertical distance. This is going to be my vertical displacement delta y. However, we are starting up here and moving downwards. If you're moving down, that's the negative direction, so I have to make this negative 50 meters. Now this is how far we're moving to the right. This is a horizontal displacement, and this is going to be called delta x. Now, as far as our equations are concerned, in the conceptual video, they talked about how the horizontal motion, the vertical motion, are not connected to one another. The horizontal motion is not accelerated, so we can take the definition of speed, velocity equals displacement over time. What I can do with this is write it in terms of delta x. In the x direction, the speed is constant. So however much speed it had horizontally to begin with, that's never going to change. That's why we can just multiply this number times t, because this technically is the average velocity, but if it never changes, your initial velocity is the average velocity. This is the one and only equation you will ever need for horizontal motion. Now in the vertical motion, it's accelerated motion, and we can use the same exact equations we use for free fall. This is maybe a little new to us, but the other ones we did before. In this case, what we're looking for is Vox. That's what we need to know. And we do know delta x. We know that that's 90 meters, but we have no idea about the time. In order to find the time, we're going to need an equation that takes what we know and allows us to solve for time. Now, it doesn't look like we know much as far as the vertical motion is concerned, but we do actually know quite a bit. One of the things you always have to do in projectile motion problems is find these components of this initial velocity. This is horizontal launch, so Vox is just going to be our initial velocity. But V0y, because it's a horizontal launch, is just 0. So we do know the initial velocity in the y direction. We also know g, negative 9.8 meters per second squared. So we know a lot more than we thought we did. And now, since we know the acceleration and the initial speed and the displacement, solving for time would probably make sense to use this equation, which we used for free fall quite often. And the thing that's going to be a little different here is, you notice I'm putting y's and x's next to our subscripts, because this motion is completely independent. The x motion and the y motion is completely independent. We have to let ourselves know which components we're talking about. And all the equations that we use for the y direction will only involve the y components of velocities. And for the x direction, only the x components of velocities. This will make more sense as we get through the problem and do maybe another practice problem. So here's the equation we have. One thing that we do know is that since Voy is 0, this whole term is going to disappear and go to 0, which means that delta y equals 1/2 gt squared. We can solve that for t, and this is the kind of key to our problem. We needed to know t so we can find V0x. And if I do that and do a good job with my algebra, I get 2 delta y over g. Now I can plug the numbers in. And that's going to be 2 times negative 50 meters all over negative 9.8 meters per second squared. Now you kind of see why we had to make our displacement in the y direction negative, because we needed that negative to cancel out this negative so we don't wind up taking the square root of a negative number. And if we do that, we get the value 3.19 seconds. And again, notice that the only thing this time depends on is the height of the cliff. It's completely independent of how fast our motorcycle is going. Okay, so now that we know this, we can combine that with this equation to find that speed. So Vox, which if you'll recall is how fast the motorcycle is going, right, is going to be equal to delta x over t. Delta x was 90 meters, and t is 3.19 seconds, which gives us a speed of 28.2 meters per second.